All right. So today we're going to delve into arguably the most complicated topic of the chapter, and that is how to differentiate a reaction going through an SN1 pathway versus SN2 versus E1 versus E2. So how do we know which of these four pathways will be the major pathway? So the first thing I generally do when I'm looking at a reaction is I ask myself, is it a good nucleophile? Is it a good base? Or is it a good nucleophile that's also a good base? Or is it a bad nucleophile and bad base? And we kind of went over that a while ago, but let's make some lists. So let's first do good nucleophile that's a bad base. So a good nucleophile that is a bad base would be something that has a negative charge, but doesn't really want to steal a proton very much. Does anybody remember what might be a good nucleophile, but it's a bad base? So what has a negative charge, but doesn't really want a proton? So we said sulfur nucleophiles. So any of these are pretty good nucleophiles, right? Sulfur, because it's such a big atom, doesn't really want to steal a proton back, but it's really nucleophilic because those lone pairs are out really far away from the sulfur atom trying to find something to react with. What else? Halogens. Specifically, we said chloride, bromide, and iodide. Fluoride's really not a good example here. So these are all good nucleophiles because they have negative charges, but they're bad bases because they're relatively stable and don't want to steal a proton back. All right, so this is one category. If we think about this, the fact that it's a bad base rules out what sort of reactions? Elimination. So we could say this means that it's not likely to do E1 or E2 because we need a base for E1 or E2 chemistry. All right, so that means it must be SN1 or SN2. That kind of limits it. So let's make a note. Okay, so let's look at our substrates. And the substrate, if you remember, is just our thing with our leaving group off of it. So we could have a methyl substrate, we could have a primary substrate, we could have a secondary substrate, we could have a tertiary substrate, and we could have a substrate where if the leaving group were to fall off, we would have resonance. All right, so let's think about this. We've got two different trends. Which of these is most likely to do SN2? Methyl and primary, right? In fact, SN2 is going to be a lot faster with a methyl substrate than a primary substrate. Why is that? It's less bulky, right? It's less hindered. So methyl substrates are definitely going to do SN2. Which ones will do SN1? Okay, so then we'd say SN1 is likely for tertiary and resonance. And we said that the reason for this is it's way, way too hindered to do SN2 on a tertiary carbon, right? So it's not going to do SN2, but it's stable as a carbocation. Resonance is a little bit tricky. I'm going to make a note down here. It can do SN2 if primary. So resonance, if it's still primary, can do SN2. This is kind of an either or situation. Oh, sorry, can do SN2. Sorry about that. All right, what about in this middle spot right here? What can secondary do? Can do either. How do we know if it's going to do SN2? What's another thing we can look at? Solvent. So solvent choice matters. If we have protic, meaning it can H-bond, what's it likely going to be? SN1. Aprotic must be SN2 then. Like we said, protic solvents are nice for SN1 because it kind of catches the leaving group as it falls off, stabilizes it with H bonding, where aprotic solvents are good for SN2, because we don't want the solvent to interact with the nucleophile as much. So really when we look at this, this is due to steric accessibility. And this over here is due to carbocation stability. So this is what we covered a fair amount in our previous chapter, was kind of how to decide whether or not something's going to be SN1 or SN2. All right, so that's a relatively easy example, but let's go on to the next one. Let's consider if we have a good base that's a bad nucleophile. All right, what's some examples of something that's a good base but a really, really bad nucleophile? So I heard somebody say the tert-butyl one. So tert-butoxide, why is this a bad nucleophile? It's too bulky, right? What's another one that's a bad nucleophile? DBN and DBU. Those were our special ones. Those were the bicyclic ring systems that were massive. They're not going to be very good nucleophiles. What else? Hydride. So anything with H minus. Why isn't this a good nucleophile? It's not soluble. And then the last one is LDA. That's the lithium diisopropyl amide. It's got 2 isopropyl groups hanging off of it. It's massive, just not going to do any sort of nucleophilic chemistry. So if we think about this, this gives us a few clues. If it's a bad nucleophile, what is it unlikely to do? Okay, so it's not likely to do SN1 or SN2 because it's a bad nucleophile. Conversely, this tells us that it must do elimination. All right, so that's a pretty big clue. Now let's consider our substrate. Again, we can say, all right, what if we have a methyl substrate with the leaving group? What if we have primary? What if we have secondary? What if we have tertiary? And what if we have something with resonance? All right, let's consider the first one, methyl. So what if I have something like this, that's a methyl group and a leaving group, and I treat it with hydride, H minus. What sort of elimination chemistry will this do? Will it do E2? Ah. Does anybody see a problem? Where are my beta protons? Oh, I don't have any beta protons. If we look at these protons right here, these are coming off of the alpha carbon. Can't do E2 chemistry without beta protons. So what we could say is with this one, that there is no reaction because there are no beta protons. So a little bit tricky for that one, but it's important to remember with E2 or E1 chemistry, we have to have beta protons. In that case, we wouldn't. All right, let's do the next one. What if we have, let's say, this group, and we treat it with hydride? If we look at this carbon right here, this is a primary carbon. What sort of chemistry will this do? Will it do E1 or E2? Let's think about it. What's the big difference between E1 and E2? The base. For E2, do we need a strong base or a weak base? Strong base. For E1, do we need a strong base or a weak base? Weak base. In this case, we're saying all of these are strong bases, which tells me that this must be E2. What about the secondary? E2. What about tertiary? E2. What about resonance? E2. However, we must have beta protons in all of these examples in order for E2 to occur, right? Yep. So if we have a bad base, what sort of reaction might we get? E1, and we'll cover that a little later. But all of these, like we set up here, are going to be good, strong bases. So we're going to consider the fact that all of these would do E2 chemistry. Okay, so it's important to note, for for all of these that you must have beta protons. So I'm going to put an asterisk on all of these and say must have beta protons that are anti-coplanar. If we don't have an anti-coplanar beta proton, we can't do any of these E2 reactions. All right? My question for you is, let's kind of take a zoom in look on these. Which of these will do the fastest E2 chemistry? Primary, secondary, or tertiary? If we think about substitution, which one will give you the more substituted alkene? Tertiary. So we said yesterday the other thing to consider is between these, this will be faster E2 because it'll lead to a more substituted alkene. And we said that that has to do with the hyperconjugation that's occurring when we make these double bonds. We really like making more substituted alkenes when possible because that has a lower energetic barrier. Does this make sense? So these are pretty easy. If we look at strong bases like these, always going to do E2. All right, now we get into the tricky ones. What if we have a good nucleophile that's also a good base? What are some examples of this? Hydroxide, right? Because it's not very bulky. Another one might be OME, that's methoxide, or OET, that's ethoxide. All of these are much smaller than a tert-butyl group. So they're going to be good nucleophiles and good bases. All right? So if it's a good nucleophile, what does that tell us? Is it likely going to do SN1 or SN2? Yeah, SN2, we need good nucleophiles. Did nucleophiles really matter very much for SN1? No, it wasn't involved in the rate limiting step. All right, however, over here, we're saying that these are also good bases. What does that tell us? Will it do E2 or E1 if it's a good base? E2. All right, so now we've got this debate. Is it going to be SN2 or is it going to be E2? All right, so let's go ahead and make our list of substrates again. We've got methyl over here, got primary, got secondary, got tertiary, and we've got resonance. All right, let's first start with methyl. If we have a methyl substrate, which do you think will occur, SN2 or E2? SN2. Why won't E2 occur? No beta protons. In fact, we just said that up here, right? With E2 chemistry, you need to have beta protons. So if we look at this one, we could say methyl group is going to be SN2 only because there are no beta protons available for E2 chemistry, right? All right, let's go over to primary now. Primary gets a little tricky. Can it do SN2? Well, let's go up and check. Up here, we said that primary carbons with good leaving groups and good nucleophiles can definitely do SN2, right? Not going to be as fast as a methyl group, but it can definitely do that. So let's make a note here, and we'll just say, all right, for a primary carbon, SN2 is okay. What about E2? It's possible. So I'd say SN2 and E2. All right. What about secondary? Can secondary carbons do SN2? Yes. Can it do E2? All right. What about tertiary? No SN2. So this would be E2 only because it's too hindered. All right, what about resonance? Well, it depends for resonance, right? So if we think about resonance, resonance can be a primary carbon, which can do SN2. So I'll just say SN2 if primary. However, it's likely not going to do SN2 if it's secondary. However, E2 is definitely possible. All right, so now my question for you is, if we think about SN2 rates, which ones are going to be fastest? Okay, so we'd say SN2 faster because methyl and primary is better. All right, what about E2 rates? Which one's faster for E2? Why is E2 faster when we get to things like secondary and tertiary carbons over primary? We result in getting a more stabilized alkene, right? So we've got two competing trends. All right, so now what we need to do is we need to look at these situations where we get mixtures. They're not always going to be a perfect 50-50 mixture, right? So let's focus on this first one. Which one do you think is going to be our major product? SN2, why? Because it's faster. Exactly. So up here I'm going to do SN2 major, and then E2 would be my minor product, simply because the SN2 reaction is outcompeting the E2 reaction. Make sense? All right, let's do this next one. Which one's going to be faster, E2 or SN2?
They're going to be roughly the same.
Not necessarily. Is a secondary carbon really that great for SN2? Not really. So in this case, I would say because it's not great, this would be SN2 minor, and then E2, what would it be? Major. So a lot of this really depends on the situation. If we've got a primary carbon, we're really going to favor formation of the SN2 product, not the E2 product. Does that mean we won't get any E2 product? No, we'll just get a little bit of it. If we've got a secondary carbon, we're going to get a lot of our E2 product, but very little of our SN2 product, simply because it's sterically a lot harder for that nucleophile to get in. So really the key with this is that it all comes down to this rate competition, right? Whichever one has the lowest activation energy is going to occur at a faster rate and outcompete the other one towards formation of products. So it is a little bit tricky. All right, let's do our last one. What if we have a weak base that is also a weak nucleophile? And let's come up with some examples of these. What are some weak bases that are also weak nucleophiles? Water. And really any alcohols. You notice how these are neutral. They don't have negative charges, meaning they're not going to be very good bases. And because they don't have negative charges, they're not going to be very good nucleophiles either. Okay, so let's think about it this way. We've got a weak base. If it's a weak base, will it do E2? No. We need a strong base for E2. So that tells us that this would be potentially E1. And then if it's a weak nucleophile, is it going to be SN2 or SN1? More likely to be SN1. All right, so in this situation, we could get E1 or SN1, right? All right, so now let's focus on our substrate. Let's go ahead and again write down methyl, got primary, got secondary, got tertiary, and we've got resonance. All right, let's take a look at the methyl one. Is this going to be very good for E1 or SN1? Why not? Well, we said no E1 because it doesn't have beta protons, but why not SN1? It's really, really unstable as a carbocation. So down here we would say no reaction. It is too unstable. All right, what about primary? I would really say definitely, let's just write no reaction. Again, it is generally too unstable. The only exception to this is if it's a primary carbon that is also stabilized via resonance, right? If it's a resonance stabilized primary carbon, that kind of trumps the primary nature of that carbon. All right, so no reaction for these. Both of those are simply too unstable to really support formation of that carbocation. All right, now let's think about secondary. So secondary carbon, can a leaving group fall off? Yeah, it's possible. We saw that, in fact, up here, where we said it could do SN1 in particular in a protic solvent. So down here we could say, all right, SN1 is possible. What about E1? Is E1 possible? Yep. What about with tertiary? Could do both of them. What about with resonance? Which one's better, secondary, tertiary, or resonance? I would say resonance, right? Because the rate limiting step is formation of that carbocation. So this occurs at a faster rate due to the more stable carbocation. All right, now the question is there a competing rate trend we really need to think about for SN1 versus E1? Are the rate limiting steps different for SN1 and E1? They're the exact same rate limiting step. So up here, we said that these rates were actually different. Down here, the rate trends are going to be exactly the same, meaning you're typically going to get a mixture of these all the time. It's very, very hard to exclusively get E1 over SN1. All right. However, there are some tricks. How can we favor E1 over SN1? Heat. Why? Why does heat favor SN1 over E1? Entropy, right? We saw it in an elimination reaction. They're favorable under high temperature conditions because we're creating more moles of products than we have of starting material, where with SN1, the number of moles really doesn't change. So heat is a big thing you can look at. How about in lab? Oh, sorry. Oh my goodness. This is a problem with talking and writing. E1 over SN1. Thank you. So heat favors elimination over substitution due to entropy. All right. So let's think about lab. In lab, we were working with cyclohexanol, and we dehydrated it and made cyclohexene. We didn't run into any of the substitution problems. How was that able to work? We did apply heat, right? We distilled it. But what was kind of unique about that reaction, too? We didn't use base. We used a catalyst, right? So second note is secondary or tertiary alcohols plus catalytic acid. And typically this catalytic acid is one of two different acids, or sometimes three. It could be H2SO4, that's sulfuric acid, or phosphoric acid, which is H3PO4. Those are typically pretty common. Sometimes you see tosylic acid, however, that's a little less common. And you apply heat, which I'll show with that delta symbol. We get E1 exclusively. So you can actually use this to exclusively get E1. No SN1 will result out of this reaction, which is kind of nice. Does that make sense? All right. So let's really quickly summarize what we've kind of covered. So yeah, so the question was, is there any way to get SN1 exclusively? Not that I know of. You'll typically get an E1 SN1 mixture. All right, so good base only. Yeah.
What is the purpose for wanting to have E1 exclusive when you're going to make the same product?
So what's the purpose of getting E1 only?
Yeah, like why would we want to do E1 only?
So let's say we're trying to make an alkene. We want to make it in the highest yield possible. So if there's a way to avoid an unwanted SN1 byproduct, we would maybe choose that method as a way of avoiding that.
Okay.
Yep. All right, so let's make a list. We've got good base only. We've got a good base and good nucleophile. We've got a good nucleophile only. And then last but not least, we've got a weak base and weak nucleophile. So these were our three main classes. What were our good bases that were only good bases again? Let's just practice. Terbutoxide. Again, that looks like this. Then we DBN, DBU, LDA, and H-. All of these won't do substitution chemistry, at least not readily. All right, what's a good base that's also a good nucleophile? OH-, OMe, OET. All of these are pretty good bases, right? They want to steal their proton back, but why are they also good nucleophiles? They're negative charged, they're unstable, and they're not very bulky. Unlike this tert-butyl group hanging off the end here, that makes this a really bad nucleophile versus these ones right here. All right, let's go to the next column. What's a good nucleophile only? We said the halogens, right? Because they're the conjugate bases of strong acids. And then we also said anything with sulfur. So something like this. And in many cases, you'll even see neutral sulfur molecules acting as really good nucleophiles, simply because they don't hydrogen bond to each other very tightly, and they'll just attack. All right, weak base and weak nucleophile. Water and any sort of alcohol, so I'll just call that ROH. Make sense? Is this an exhaustive list? No, it's just the most common ones that we'll run into. All right, I'm going to show you something that I always kind of hesitate to show my students, but you'll probably find it anyways. If you go through the book or go on the internet, you will find all sorts of flowcharts and tables where they say, all right, over here, what sort of substrate do you have? Is it primary, secondary, or tertiary? And then over here, it'll tell you, all right, are you dealing with a strong base that's a weak nucleophile, a strong base that's a strong nucleophile, a weak base that's a strong nucleophile, or a weak base that's also a weak nucleophile? And then it'll basically, you can follow the flowchart and it'll tell you exactly what sort of mixture you'll get. I have students every year that are like, this is wonderful. I'm just going to brute force memorize all of this and I'll do perfect on the exam. And it never works out well. Instead, what you really need to focus on is the thought process of that last thing we went through. So on this page, we kind of were able to problem solve things like this. So would it be SN2 major or E2 major? And we were able to kind of slow down, ask ourselves about the rate, and kind of infer which one would be fastest. So if you understand the why behind each of these, you'll be in really good shape. I've found that students that just brute force memorize flowcharts, it gets too crazy in your head. It's a lot better to understand the why and the mechanics behind everything than to just blindly follow a flowchart. So that's my advice to you as you're studying. All right, so the last piece is going to be this in-class activity. This in-class activity is actually really, really similar to one of your skill builder exercises. There are some slight differences in some of the problems, but what you need to do is you need to determine, is the reaction going to be SN1, SN2, E1, or E2 first? And then after that, give me the product or products, if there's more than one product, and try to label them major and minor as needed. So we're going to use that same sort of problem solving. This won't necessarily be on tomorrow's quiz, but it will be on the final. Make sense? All right, so let's do our poll. Since we are running out of time, how many of you would like to work on this tomorrow in class? Or sorry, not tomorrow in class, Friday, after the quiz. We don't have class on Friday, so it would be optional. How many of you would like to do the final on Friday? Oh, wow. All right. So what we'll do is, because this is confusing, what I'll do is I'll make a video key where I kind of walk you through the problem-solving steps for each of these. But what I would do is, between now and the final exam, sit down, try to really push your way through this entire worksheet. It gets progressively more challenging as you go through it. And then when you're done, if you're stuck, check the video, check your work and make sure that you did everything correctly. If you're maybe reaching the middle and you're like, I'm completely lost, then turn on the video and maybe watch part of it, but not all of it. Try to make sure that this is a challenging worksheet. This is an excellent way of preparing yourself. All right, on Friday too, if you can't make it to the final exam review because it's not a scheduled class day, I'll record that as well, and I'll post that online so that you can watch the full kind of review session on your own time, but you don't have to necessarily be here if you can't make it due to work or other obligations.
What time will it be on Friday?
1:30 on Friday will be our final exam review. All right, any other questions before we do small group work? All right, let's try to start working on this.